Microservices Architecture. Microservices architecture is a design approach in software development where a large application is divided into small, independent services. Each service, or microservice, is focused on a specific business capability and can be developed, deployed, and scaled independently. This contrasts with the monolithic architecture, where the entire application is built as a single unit. Key concepts of microservices architecture. 1. Service independence. In microservices architecture, each service operates independently. This means that changes to one service do not affect others. Services communicate with each other through well-defined APIs, application programming interfaces, often using protocols like HTTP REST or gRPC. 2. Decentralized data management. Each microservice typically manages its own database, leading to a decentralized approach to data management. This avoids the need for a central database, which can become a bottleneck in monolithic systems. Each service can use the most appropriate database for its needs, whether relational, NoSQL, or others. 3. Scalability. One of the most significant advantages of microservices architecture is the ability to scale services independently. If one service experiences high demand, it can be scaled up without affecting other services. This granular scalability is crucial for handling varying loads across different parts of an application. 4. Fault isolation. Microservices architecture enhances fault isolation. If one microservice fails, it does not cause the entire system to crash. This is because each service is isolated and can fail independently, reducing the overall system's vulnerability. 5. Continuous deployment. Microservices allow for continuous deployment and delivery. Since each service can be updated independently, new features or fixes can be deployed quickly without waiting for a complete system overhaul. This aligns well with DevOps practices and the need for rapid iteration in modern software development. 6. Technology diversity. Microservices architecture supports using different technologies for different services. For example, one service might be written in Python, while another might use Java, depending on the specific requirements. This flexibility allows teams to choose the best tools and technologies for each task. 7. Communication. Microservices communicate with each other over a network, often using asynchronous messaging or synchronous calls via APIs. Asynchronous communication, often implemented with message brokers like RabbitMQ or Kafka, allows services to operate independently of each other's timing, further decoupling them. Real-life use cases and examples. E-commerce platforms. A large e-commerce platform might use microservices architecture to handle different aspects of its operations. For instance, the product catalog, user management, order processing, and payment systems could each be a separate microservice. This allows the platform to scale efficiently during peak shopping seasons, like Black Friday, without impacting the overall system performance. Netflix. Netflix is a prime example of microservices architecture in action. The streaming giant moved away from a monolithic architecture to a microservices-based approach to handle its massive user base. Each function, such as user recommendations, content delivery, and account management, is handled by individual microservices. This allows Netflix to deploy updates frequently and handle millions of simultaneous users without downtime. Banking systems. In banking, microservices can be used to manage different services like account management, transaction processing, fraud detection, and customer support. This modular approach allows banks to innovate quickly by adding new features without disrupting existing services. Benefits of microservices architecture. Agility. The independence of services allows development teams to work on different parts of the application simultaneously. This speeds up development and makes it easier to adapt to changing business needs. Resilience. With fault isolation, the failure of one service does not bring down the entire system, making the application more resilient. Scalability. Services can be scaled individually, which is more resource efficient than scaling an entire monolithic application. Flexibility in technology. Teams can choose the best suited technology for each service, which can lead to better performance and more innovation. Faster time to market. Continuous deployment practices enabled by microservices allow companies to release features and updates more frequently, staying competitive in fast-paced industries. Challenges of microservices architecture. Complexity and management. While microservices provide many benefits, they also introduce complexity in terms of service management, communication, and deployment. The decentralized nature requires robust orchestration tools like Kubernetes to manage the lifecycle of services. Data consistency. Ensuring data consistency across multiple services can be challenging. This often requires careful planning and the use of eventual consistency models, which may not be suitable for all applications. Monitoring and debugging. With many small services running independently, monitoring and debugging issues can become more complex. Effective monitoring tools and practices are essential to track the performance and health of each service. Conclusion. Microservices architecture is a powerful approach to building scalable, resilient, and flexible applications. It allows large and complex systems to be broken down into manageable pieces, enabling faster development, easier maintenance, and the ability to adapt quickly to changes. While it introduces certain complexities, the benefits often outweigh the challenges, especially for organizations that require agility and scalability. Real-life examples like Netflix and modern e-commerce platforms demonstrate the effectiveness of this architecture in handling large-scale, dynamic environments.